In this video, I will cover content from Chapter 2, Section 5, where we will switch from linear equations to linear inequalities. First, let's talk about what a linear inequality actually is. A linear inequality is an inequality containing linear expressions. So if we take our linear expressions or our linear equations from previous sections and swap out the equal sign for inequality symbols, we have a linear inequality. An endpoint is a number on a number line that separates values that are solutions from values that are not. Here's what I mean by this. If we have an inequality of x is greater than equal to 3, all values of x that satisfy this inequality are values that are greater than or equal to 3. 3 in this case would be the endpoint. I also want you to notice that since we are allowing x to be greater than or equal to 3, x equal to 3 is a solution. It also serves as the number that separates values that are in the solution set and those that are out of the solution set. Let's also quickly look at x is greater than 3. In this inequality, we're only allowing values that are strictly greater than 3 to be part of our solution set. 3 here is again the endpoint because it does separate values that are in from values that are out, but in this case, x equal to 3 is not a solution. If we require x values to be strictly greater than 3, then x equal to 3 does not satisfy that requirement. Let's start by graphing some simple inequalities on number lines. In example 1, we're going to graph the solutions on a number line. I will do parts A and D and leave B and C for you. Our first inequality reads, x is greater than 2. We'll center our number line at 0 and add some positive values to the right and negative values to the left. If we want values that are strictly greater than 2, we want all values that are to the right of the number 2. Think about whether or not we want 2 to be in our solution set or not. Since we're saying x needs to be greater than 2, 2 is not a solution. 2 is not greater than 2. So we'll put an open circle on the 2, which shows us that we do not want 2, just only the values to the right of 2. Let's look at part D. In part D, we have negative 2 is less than or equal to x. You could also think of this as x values need to be greater than or equal to negative 2. Let's start with our number line. Centering at 0 with positives to the right and negatives to the left. Negative 2 is right here. If we want x values to be greater than or equal to negative 2, we want x values that are greater than negative 2, so to the right of negative 2. We also want negative 2. This time, since we have this equals included, that means that x can be negative 2, so we will fill in the circle. Filling in the circle notates that negative 2 is part of the solution set along with the values to the right of negative 2. Now let's talk about intervals. An interval is a range of values on a number line, just like what we were just drawing on our number line. Interval notation is a way to write the solution of an inequality by listing the left and right endpoints. It's important to note that we will use parentheses when we write our interval notation if the endpoints are not included as part of the solution set. We will use brackets if the endpoints are included as part of the solution set. Let's look at some examples where we'll change from an inequality to graphing on a number line and then writing with interval notation. Notice that for these inequalities, I have the same endpoint of 3. but they are all different inequality symbols. For our first inequality, we have x is greater than 3. That means that we want all values of x that are larger than 3, so to the right of 3. Also notice that there's no equal sign in my inequality, so 3 is not part of the solution set. So I'll notate this endpoint with an open circle. In interval notation, I need to write the left endpoint and the right endpoint. And since the endpoint here of 3 is not included, I need to use parentheses. The left endpoint of my interval is 3. The right endpoint of my interval is infinity. It goes on forever. So we just notate that with an infinity symbol. Infinity is a concept, it's not a number. So we always put parentheses by infinity because it's not an endpoint that we can get to and stop at. Let's go on to the second one. Now we have x is greater than or equal to 3. Again, my endpoint here is 3, and I want all values that are to the right of 3. But this time, it's okay that x is equal to 3 because my inequality says that our solutions can be greater than or equal to 3. So I will color in the endpoint. In interval notation this time, I will use a bracket because 3 is included in my interval. To the right, again, my endpoint is infinity because we go on forever, and I will still use a parenthesis next to infinity because, again, infinity is a concept, not an endpoint that we can stop at. Next, we have x is less than or equal to 3. My endpoint here, again, is 3, but now I'm requiring that my x values are less than 3. So that means I want everything to the left of 3. I also don't want to include 3 in my solution set. Now this time, 3 is my right endpoint. It's where my solution set ends on the right. To the left, we go off to negative infinity, and just like positive infinity, we use a parenthesis. Last one here is that x is less than or equal to 3. Again, our endpoint is 3, and we do want values to the left of 3. But this time, the 3 is included because of the less than or equal to symbol that's used, so we will fill in the endpoint. In interval notation, we again have a right endpoint of 3, but it's included, so we use brackets. To the left, we go on to negative infinity, and we use parentheses. Let's talk a little bit about what it means to solve a linear inequality. Solving linear inequalities is very much the same as solving linear equations like we've been doing in previous sections. The only difference is that when we multiply or divide both sides by a negative number, the direction of the inequality changes. That is, if you have a less than symbol, it needs to be swapped out for a greater than symbol. If you have a less than or equal to symbol, it needs to be swapped out for a greater than or equal to symbol. Multiply or divide by a negative, flip the sign. Let's try this out in example 2. Example 2, part A, we have 4x plus 3 is less than 31. We can almost treat this inequality symbol like an equal sign. We just have to keep in mind that we need to switch it if we multiply or divide by a negative. We will start by subtracting 3 from both sides, just like we would if this were an equation. This gives us a positive 3 minus 3 on the left, leaving us with just our 4x, is less than 31 minus 3, which is 28 on the right. The opposite of multiplying by 4 is dividing by 4. So we can isolate the variable by dividing both sides by 4. This leaves us with x on the left and 8 on the right. So now we have an equality of x is less than 8. We've now solved the inequality because we've isolated the variable. Now let's put our solution on the number line. With 0 in the center, I'll squeeze in 8 right over there. We want all values that are strictly less than 8, not equal to 8. So I'll use an open circle for the endpoint and shade everything to the left. To write this in interval notation, our left endpoint is negative infinity, and our right endpoint is 8, and we use parentheses because it is not included. Let's look at part D. We will solve part D in a very similar way. We'll isolate the x. First, we'll add 10 to both sides of the equation. When we do that, we are left with just the negative 3x on the left is greater than or equal to 17 plus 10, or 27 on the right. Right now, x is being multiplied by negative 3, so we will divide both sides by negative 3. Now, this is that moment you've got to pay attention to because we just divided by a negative. And when we multiply or divide both sides of an inequality by a negative, we have to switch the sign. So when we divide, we have x on the left, negative 9 on the right, but we must flip the sign around. So now the inequality is x is less than or equal to negative 9. Let's put this on our number line. With larger numbers, sometimes it's useful to count by 2's. Now, we start at negative 9 with our endpoint. Negative 9 is included in this solution set because we have a less than or equal to symbol. So I'll use a closed circle at negative 9. I also want all the values to the left of negative 9 because I want values smaller than negative 9. Written in interval notation, we have a left endpoint of negative infinity because we go on forever to the left. We have a right endpoint of negative 9 because that's the endpoint of our solution set. That's where it stops. But we use a bracket because negative 9 is included here. Let's take a look at example 3. The instructions for example 3 are the same as those from example 2. We're going to solve the inequality, write the solutions on a number line, and then in interval notation. The only difference is we're going to have a couple more steps to solving these inequalities. Let's look at B. In B, notice that now I have an x on both sides of the inequality, and I have constants on both sides of the inequality. Let's start by combining our variable terms onto one side of the equation. I'll do this by adding 2x to both sides. This leaves me with 4x plus 2x, or 6x on the left, minus 5, is less than or equal to negative 2x plus 2x is 0, and then I have a positive 7. Now I need to get my constant terms to the other side of the inequality. So I will add 5 to both sides. This leaves us with just the 6x left on the left, and 7 plus 5, or 12 on the right. Finally, we can isolate the x by dividing both sides by 6, leaving us with x is less than or equal to 2. Let's put these on a number line. Our endpoint here is positive 2. We also want all values less than 2. Since our inequality has equals as part of it, we want to include our endpoint. That is, 2 is part of the solution set. To write this in interval notation, we need a left endpoint of negative infinity and a right endpoint of 2. We use brackets because 2 is included. Let's look at part C. In part C, we have a little more simplifying to do on the left side and the right side before we combine like terms. On the left, we start with this 11x minus 3. It's grouped together, but there's nothing that needs to be distributed to it, so we can drop those parentheses. However, the second set of parentheses, we need to be careful and distribute the negative. Think of this as a negative 1 times 2x minus 13. Negative 1 times 2x is negative 2x. Negative 1 times negative 13 is positive 13. On the right, we can also distribute the 4 to both terms inside the parentheses. We have 4 times 2x, which is 8x, and 4 times 1, which is 4. On the left, we have some like terms that we need to combine. I'll first combine 11x and negative 2x. Having a positive 11x and a negative 2x gives me a total of positive 9x. Now I will combine the like terms, the constant terms, of negative 3 and positive 13. A negative 3 and a positive 13 totals to positive 10. Now that I've simplified both sides of the inequality, I will collect the variable terms on one side and the constant terms on the other. I'll start by subtracting 8x from both sides so that my variable terms are together. That leaves me with 9x minus 8x, or 1x on the left. On the right, I have a positive 8x and a negative 8x, which is 0, leaving me with just the constant 4. Now I can get my constant terms onto the other side by subtracting 10 from both sides. 1 times x is simply x, and 10 minus 10 is 0. So this leaves me with x is greater than or equal to 4 minus 10, which is negative 6. So now we've solved the inequality and have x is greater than or equal to negative 6. All of the solutions to this inequality are values that are greater than or equal to negative 6. Let's graph this on a number line. Since we have an equal sign as part of our inequality, we want a closed circle at negative 6. We also want all x values that are greater than negative 6, so that's all values to the right of negative 6. Now we can write our solution in interval notation by using a left endpoint of negative 6 and a right endpoint of infinity. Negative 6 is included in the solution set, so we use a bracket. Infinity, again, is a concept, not a number, so we use parentheses. Now we're ready to move on to compound inequalities in example 4. A compound inequality is two or more individual inequalities together. So in example 4, you'll notice that we have two inequalities and we have the word or in between. That means that our solutions can satisfy this inequality or they can satisfy this inequality. It doesn't have to be both. Let's solve each of these inequalities separately. First, we'll start with 3x minus 2 is less than or equal to 10. To isolate the x, we'll start by adding 2 to both sides. This leaves us with just 3x on the left and 10 plus 2, or 12, on the right. Dividing both sides by 3, we have x is less than or equal to 4. Now let's solve the second inequality. We have 4x minus 13 is greater than or equal to 15. Adding 13 to both sides, we have 4x is greater than or equal to 28. Dividing both sides by 4, we have x is greater than or equal to 7. Again, we have this word in between, or. That is, solutions to this compound inequality are values of x that are less than or equal to 4 or greater than or equal to 7. Let's see what that looks like on a number line. Starting with our inequality of x is less than or equal to 4, that means x could be 4 or anything less than it. Our second inequality says that x can be greater than or equal to 7. That is, x can be 7 or anything greater than it. This is our solution set on a number line. We're okay with all x values that are less than or equal to 4 or greater than or equal to 7. Values can be anywhere in the shaded regions, 4 or 7, and be part of the solution set. Let's write this now in interval notation. Starting from the left, we have negative infinity. our values go all the way up to 4 and then stop, including the 4. Our solution set starts up again with an endpoint at 7 and then goes to positive infinity. The way that we represent OR is with a union symbol between our two intervals. This reads negative infinity to 4, union 7 to infinity. Or x can be less than or equal to 4 or greater than or equal to 7. Let's look at example 5, which is a little bit different. In example 5, these are also compound inequalities, but notice that rather than two separate inequalities with an OR in between, we have this inequality and this inequality. They're all written together. The type of compound inequality in example 4 corresponded to the word OR. These types of inequalities correspond to the word AND. That is, x needs to satisfy all parts of this inequality at the same time. When we solve this type of compound inequality, we use the same steps that we would with equations. We just have 3 sides to do the same thing to, rather than 2 sides. Let me show you what I mean. Our goal is to isolate the variable x right here in the center. The first thing I'll do to do that is subtract 1 from all 3 sides of the inequality. When I take negative 11 and subtract 1, I have negative 12. When I have a negative 1 and a positive 1 in the middle, that's 0, leaving me with just 4 times x. And on the right, I have 7 minus 1, or 6. X is currently being multiplied by 4, so to undo that, I'll do the opposite and divide by 4. And I'll make sure to do that to all 3 sides of the inequality. Negative 12 divided by 4 is negative 3. 4 divided by 4 is 1, so we just have x in the middle. And 6 divided by 4 we can simplify by dividing both top and bottom by 2. 2 goes into 6 3 times, 2 goes into 4 2 times, and so we have 3 over 2. Now we have solved this compound inequality. We have isolated the variable. This reads that x needs to be greater than negative 3, but less than 3 over 2. We need to satisfy both of those conditions at the same time. Let's draw this on a number line. Our leftmost endpoint is a negative 3, and it is not included in the solution set because this is a strict inequality. Our rightmost endpoint is 3 over 2, 3 halves, which is 1.5. So our right endpoint is right here. It is also not included in the solution set because of the strict inequality. What we want are all x values between those two endpoints. Writing this in interval notation, we have a left endpoint of negative 3 and a right endpoint of 3 over 2. We will use parentheses on both sides because neither of the endpoints are included. Let's finish this section with some word problems that involve inequalities. In example 6, I will look at parts A and D. Part A reads that students who have no more than 60 semester units completed are eligible for priority registration. Set up an inequality that shows the number of semester units for which students are eligible for priority registration. We need to represent the idea of no more than 60 using interval notation. That is, our value for the number of units needs to be no more than 60. The units could be less than 60. A student could have exactly 60 units completed and they would be eligible. So the number of units needs to be less than or equal to 60. Let's look at D. Part D reads that we have a bowler that needs to have an average of at least 200 in the qualifying 3-game series to be eligible for the final tournament. If Tim scored a 204 and a 216 in his first 2 games, what scores in the third game will make him eligible for the final tournament? Let's write down what we know. We know that this bowler needs to have an average of at least 200. That means his average needs to be 200 or greater than or equal to 200. Now, average is calculated by taking the 3 scores, adding them together, and dividing by 3. We know his first 2 scores. His first 2 scores are 204 and 216. We don't know the third one, so I'll write that as an X. Now we have an inequality that we can solve. Let's start by getting rid of the 3 in the denominator by multiplying both sides by 3. That will simplify the 3's on the left, leaving us with just the numerator of 204 plus 216 plus x. On the right now we have 200 times 3, or 600. Combining like terms on the left, we can add 204 and 216 to get 420. Subtracting 420 from both sides gives us that x needs to be greater than or equal to 180. We've solved the inequality. So now we know that Tim needs a score of at least 180 to qualify for the final tournament. And that completes Chapter 2.